which is oxidative phosphorylation in chapter 19. But before that, I'm going to review a little bit about redox reactions and reduction potentials. Today's the last day to give me an exam for grading. So that's slide. All right, so where are we? We've done all these pathways from glucose down here to the citric acid cycle and things that connect to the citric acid cycle. But what we're trying to finish is this reaction. So we've got the 6 CO2s, right? Pyruvate dehydrogenase and the citric acid cycle made the 6 CO2s. The other part of it is the 6 molecules of oxygen to make 6 molecules of water. And so oxidative phosphorylation will finally finish this, and we'll finally use oxygen and make some water. So in this picture, here's the citric acid cycle. I think I said it in this picture. The picture they're calling this energy metabolism, but I think they mean oxidative phosphorylation. So that's what we're going to sort of fill in. So the other thing is we've done a lot of these things, but one thing we haven't done yet is inorganic cofactors. So a lot of redox reactions involve inorganic cofactors like iron, and that's the most important one. So we'll do inorganic cofactors. Okay, so let's look at this reaction. So what we've done is we've taken glucose, which in the open chain is an aldehyde and a bunch of alcohols. And we've made it into 6 molecules of carbon dioxide. So obviously that's an overall oxidation reaction. Let's see what's next. One question that you might address at home is how many electrons have been removed. So you could either count NADHs, there's a whole bunch of them now, or you could approach it the following way. So this is from chapter 13, I think, this figure, which shows the oxidation states of carbon, which I think I went over long ago. And they assign an oxidation number to the carbon atom, which I think these numbers are maybe different than what you learn in chemistry, but their relative values are the same. So they assign the oxidation state of carbon to CO2 as 0, and it's 8 in methane. So if you look at the carbons in glucose, 5 of them are alcohols, and 1 is an aldehyde. Actually, the alcohols are not all the same. This alcohol, the oxidation number is 5 by this steam. Right? It's C6 has structure as shown there in the red box. So that's 5. This one is 3. Okay, that's the aldehyde. These other guys, you actually would say they're all 4. So you'd say those are the oxidation numbers of the carbons, and they're all going from 3, 4, 5 to 0. So if you add it all up, you've got 1 carbon that's 3, 4 are 4, and 1 is 5, and that I hope that adds up to 24. So there are 24 electrons. So if you count NADHs, etc., you have to take 24 electrons out of these alcohols and aldehyde to make the 6 CO2. So where are those electrons? Those electrons are all in the form so far of NADH and FADH2. Right? So the NADHs came from citric acid cycle, and NADH came from pyruvate dehydrogenase, and NADH came from glycolysis. And again, of course, later on we'll see that fatty acids also give rise to NADH and FADH2. Right? So all these electrons have been collected in the form of NADH and FADH2. And so the issue is, what are we going to do with all those electrons? So what we're going to do with all those electrons is, let's consider now, for now, only the NADH. electrons are going to be given from NADH to oxygen. And to make this balance, we could write that 2 NADHs plus an oxygen will give an NAD plus. We get 2 waters, and we need 2 more protons. So we could write this as the balance reaction. So this is a reaction by which the NADH that was made in all the metabolisms we've been covering, that's how that NADH will be reoxidized to NAD plus using oxygen. So is that shown down here? Yeah, that's sort of shown here where oxygen is going to be reduced to water using those electrons. And then again, remember from this standpoint, water is the waste product, and oxygen is the terminal electron acceptor. And so for aerobic organisms, O2 is the terminal acceptor. Okay, so this red box surrounds the electron transfer and oxidative phosphorylation system or process. Let me jump ahead. All right, let me use this cartoon to sort of summarize what happens. So first of all, this reaction of getting electrons from NADH to oxygen. So this reaction is 4 electrons. The process by which that happens is called the electron transport process. This reaction overall has a delta G0 prime, something like minus 219 kilojoules per mole. So a very highly exergonic reaction. Free energy becomes available to do work. So in this cartoon, the first part of the process is the electron transport chain getting electrons to oxygen to make water. Provides energy to do work. What's the work that gets done? The work that gets done is to pump protons across the membrane. Right, so that's part 2. So coupled to electron transport is proton pumping across the membrane. You take protons from where they're at a low concentration and you move them to where they're at a higher concentration. So there's a low concentration here, you move them to a higher concentration, you have to do work to do that. But again, you've got energy to do the work from the reduction of oxygen. All right, now once you've got all these protons on the other side of the membrane, if you let them go back through the membrane, that's going to be that process will have a negative free energy. So the next thing is for the protons to flow back across the membrane. This process has a negative delta G, so it provides energy to do work. You don't want them to just flow randomly through the membrane. You want them to flow through in a controlled way, so they flow through this pink thing. So it's a hole that allows the protons to go through the membrane again. Again, that proton flow is spontaneous, negative delta G. And this provides the energy to make ATP. So you use this free energy to do this reaction. To make ATP. And I didn't leave room to write it, but you recall that the free energy of that reaction is plus 30.5 kilojoules per mole. Okay, so that's going to be the 4th part. Today I'm going to begin addressing electron transfer. Next time we'll get into how protons get across the membrane. And then finally we'll address ATP synthesis. Okay. So, all right, if we're going to talk about electron transfer, I should review electron reduction reactions or redox reactions, and I should remind you about reduction potentials, because reduction potentials are finally relevant here. So let me do that. So this can be a little bit of a Bchm 271 again. Everybody sounds very excited to hear that. So I'm going to consider a very simple redox reaction. Let's consider this reaction. Iron plus 2 reacting with a proton to make iron plus 3 plus half a mole of hydrogen gas. So this is a redox reaction, and electrons are going from the iron plus 2 to the proton. So the iron plus 2 is the source of the electron. So it's the reducing agent, or you could call it the reductant. So the iron plus 2 gives up an electron, and therefore it becomes oxidized during this reaction. So iron plus 3 is more oxidized than iron plus 2. H plus is accepting the electron. So therefore it is the oxidizing agent, or the oxidant. And by accepting that electron, it thereby becomes reduced during the reaction. And so H2 gas is, you could say, is a reduced proton, or reduced protons. Okay, so if you were interested in studying this reaction, if you wanted to know the spontaneous direction of this reaction, you'd have to know, of course, the delta G0 prime. You'd have to know the sign of the delta G0 prime for the reaction. If you wanted to know, if you had a mixture and you wanted to know how far from equilibrium is it, or how much of the concentration is going to change until you get to equilibrium, you know, the magnitude of delta G would tell you something about how far you are from equilibrium. Okay, so that's a very simple redox reaction. So the remarkable thing about redox reactions, as you know, is that unlike every other reaction we've done so far, where if you have two reactants, they have to be right there next to each other, a redox reaction, you can separate them in space, right? So you can set up two beakers, and in one beaker, you can put iron, and in the other beaker, you can have protons and hydrogen gas. And as long as you connect these by a wire, electrons, maybe the iron plus 2 might give up an electron, and an electron can flow through the wire and come over to here and react with the H plus. Or it could be the opposite, right? The H2 could give up an electron. Electrons might flow from left to right. Again, you'd have to figure out the sign of delta G to know what's going to be the spontaneous direction of this reaction. Right? So this is sort of a battery or an electrochemical cell. Remember that to complete the circuit, you need a salt bridge, which just makes sure that that the overall charge doesn't change. If it did change, then the electrochemical cell would stop. All right, so here's the picture from the book that shows this. And so in this picture, yeah, so let's assume that the iron is on the right side and the hydrogen is on the left side. All right, so it's the question of which direction are the electrons going to go. To decide that, we still have to know what delta G is. How can we figure out what delta G is? Well, this is going to be an electrical current. And you could say that the force that causes that current to flow is called the electromotive force, or it's a voltage. So voltage is, in a sense, the force that causes electrons to flow. And the nice thing is that we can measure the voltage. If we put a voltmeter in here, so there's an old-fashioned analog voltmeter like this one here, and the voltmeter can measure the electromotive force that's causing it. All right, so let's see. So the voltage tells you the same things as free energy, and as you'll recall, I'll remind you of the equation that relates them. But the voltage can be positive or negative. So positive might be that electrons flow from the iron plus 2 to the H plus, or it could be the other way around. It's not important. But you'll get a negative if the electrons go from H plus to the iron, or actually be going from H2 iron, right? So depending on which direction the electrons are going, the voltmeter is going to give you a negative or positive voltage. And the magnitude of the voltage is going to be related to how far from equilibrium it is. If the system is at equilibrium when you start it, the voltage will be 0. There's no flow of current, and the voltage is 0. Right? So voltage is telling us the same thing as free energy, because in a sense they are the same thing. And you remember now that the voltage, which you can measure, which we call, I'm going to call it delta E0. Sorry. Well, we'll define it as delta E0. And you recall that we can relate delta E0 to the free energy of the reaction by delta G is, delta G0 is equal to minus N times F times delta E0. All right, so this is, first of all, it's standard state. So this would be the voltage that we would measure if we had a mixture that had 1 molar H plus, 1 atmosphere of H2, and 1 molar of each of these in the other beaker. Right? So if we set up a system as its standard state, and we stick the voltmeter in there, the voltage that we measure should be equal to what we would call delta E0. Now what about the rest of this equation? N, remember, is the number of electrons. And N depends partly on how you write the reaction. So the reaction I wrote up here, N is 1. Where did I write it? 1 electron has to go from the Fe to the H plus for this reaction. Right? So N is 1 the way I wrote it. You could write it as 2 Fe2s plus 2 protons gives 1 mole of H2, in which case N would be 2. And what is F? F is really a conversion factor that converts from units of volts to units of kilojoules per mole. So what is the value of F? Remember it? You could use 96.48 kilojoules. Kilojoules per volt per mole of electrons. And so N is the number of moles of electrons, and delta E gives units of volts. So this conversion factor gives you units of kilojoules per mole on the left side. So you all remember this equation, and maybe you remember where it comes from other than me just telling you. So that's great. All right, so let's go back to this equation, and let's analyze it the way you do in electrochemistry. And let's remember that, like any reaction, we can always write the reaction as a sum of two individual reactions. In this case, of course, the reactions we write are half reactions. So we can write this as a sum of two reactions, iron plus 2 going to iron plus 3 plus an electron. And then the second reaction is proton plus an electron to give half a mole hydrogen. Right? So this reaction up here, should be a star, is those two reactions together. It's a sum of those two reactions. So if we wanted to know the delta G of this reaction, well, it would be the sum of the delta G. Let's keep it as delta G for now, not delta G zero prime for now. Delta G of this reaction, call it, give it that subscript, and the delta G of this reaction. And so this delta G would be just the sum of the two individual delta G's.
Does it say iron plus 4 or plus 2?
This is Fe, this is the delta G for the iron reaction. That's my subscript. So, of course, you know that you just add the free energies. Okay, so what's the reduction potential? As you know, then you can assign a reduction potential to these molecules. So the reduction potential is going to be related to the free energy change of this reaction. Right, so these are the standard reduction potentials. But you can think of it as the standard reduction potential. Just tell you about the free energy of these individual half reactions. All right, so if we wanted to figure out the delta G of these reactions, we could figure it out by adding the free energy changes of those reactions if we knew them. Right, but of course, we can also use the reduction potentials. This is where reduction potentials are useful. So let's sort of define, or remember how we define what the reduction potential is. So first of all, we define the reduction potential for a reduction reaction. Right? So when we look in the table, and I'll show you the table in a minute, the reactions in the table are all written as reduction reactions. So for example, you'll find this reaction in the table. Right? And so we'll call that the reduction potential, standard reduction potential of H plus. It's related to the free energy change of this reaction. Now this reaction, when you look for this reaction in your table of reduction potentials, you're going to find it written as a reduction reaction, so you're going to find this reaction. Right, so you will find the reduction potential of iron plus 3. Right? So these were always written as reduction reactions, so you have an oxidized form accepting one or more electrons and becoming a reduced form. Right? So that's how they're written for this case. Okay, so how are we going to use these to figure out the delta G of that reaction that I wrote? Well, so just as, let's see. Let's see, there's a couple of points I wanted to make before. So, all right, for the overall reaction, this reaction, if we knew the free energy changes of the individual reactions, we could add them together. We could do the same to figure out delta E. Right, remember, we can use the reduction potentials and simply combine them together to get the overall delta. All right, so how do you do that? If we look at the table, we'll find this reduction potential. All right, so the delta E is we're gonna take that value and we're gonna plug it in, but we're not gonna find. Oh, but the other reaction that we're gonna find is this reaction. Okay. We're gonna find a reduction potential in the table. I just wrote all this above. We're gonna find that for iron plus 3, right? But in our coupled reaction, iron plus 3 is a product, right? In the reduction potential table, iron plus 3 is a reactant, but here it's a product. So here's how you can do it, right? Very easy way to do it is we're going to have to turn this reaction around when we add these two together to make that coupled reaction, right? So it's just like free energy changes. When you couple reactions together, sometimes you have to turn a reaction around. If you do that, you change the sign of the free energy change, right? We'll do the same thing here. Just add the reduction potentials, but you're going to have to change the sign of one of them, right? Whichever reaction is, you have to turn it around. Just change the sign of the reduction potential that you find in the table. Okay? And so that's the equation that you can use to figure out the delta E for this reaction. Right, now another way to think of it, which is exactly the same thing, is you look at the reaction, and this is E0 of the oxidant in the reaction, right? H plus was the oxidizing agent, right? And you subtract from that E0 of the reductant, right, where iron plus 2 is a reducing agent of reductant. Right? So if you want to memorize it this way, I think this should give you the right answer as well. Right? But this way I always think is more intuitive because it's exactly like how we're used to dealing with energy. Okay, so today we have a table we can look at, but suppose we didn't have that table. If we wanted to figure out delta E, we would have to know this value, and we would have to know that value separately. Right? So how can we know those two values separately? The answer, as you may remember, is we can't. It's like for delta G is the free energy of the products minus the free energy of the reactants. Right? We can't know that. There are ways we can figure out the difference, but we can't know the individual. This is G, not delta G. Right? This is E, not delta E. So we can't know these. There's no way to measure them individually, right? All we can do is measure the difference. So how do we get around this? We define the reduction potential of a proton is 0. Okay? Once we've done that, then we can figure out the reduction potential of everything else we want to figure out. All right? So if we define this one as 0, for example, we could figure out what the reduction potential of iron plus 3 is. How would we figure it out? Well, it turns out that for this reaction that I wrote up above, delta E, if you measured it, would be equal to minus 0.771 volts. How do I know that? Because I looked up the answer that I want. Right? But let's turn it around. So this is equal to the difference in the reduction potentials of these two things. We don't know these separately, but we're going to call this one 0. All right, so that allows us to figure out the other one. All right, so now simple calculation. The reduction potential of iron plus 3 is equal to plus 0.771. So that definition of defining the reduction potential of the proton as 0 gives us a standard, and then we just compare every other substance in the universe to that standard. Right? Okay. So this has been done at great length, great many experiments over many years, and it leads to a table like this one. So this is the table in chapter 13. It lists reduction potential, standard reduction potentials for a great many substances, great many half reactions. And a lot of these are going to be relevant in oxidative phosphorylation, some of them. And I'll point this out. So this is a big table, so let me just compress the table a little bit. I just want to point out a few things about it. I guess I should go back. So these are E0 primes, right, biochemical standard state. Note that here's the proton reaction I've been talking about. This is actually E0, right? This is at pH 0, 1 molar protons, right? So there it is, defined as 0. Right? Now, for that reaction, if you want to figure out what is at pH 7, you have to apply a correction factor. So let me remind you how we can correct to other conditions. So for delta G, we can correct for other conditions by this equation. Right? So this is the delta G for standard state, and then this Q, whatever its magnitude is, allows us to correct for or calculate for a different set of concentrations. So remember that the equation for delta E is, I'll step in the way. The equation for delta E is that delta E under any conditions is equal to delta E0 plus, I got to get it right, RT over N times F, where N and F mean the same thing as they meant earlier, times the log of Q. And so that's an equation that allows us to correct for anything we want. All right, so you could use this equation to correct the E0 value for a proton. Right? So I'll write it as written on the slide, 2H plus 2 electrons to give a mole of H2. So delta E0 is equal to 0, right? These are the reactants and products. I guess you ignore the electrons as a reactant. But you could use this equation to calculate what it should be at pH 7. Right? It's just, Q is going to have 10 to the minus 7 in it. If you do that, you can do it at home if you want, you'll get a different value for here it is here. All right, so here's the proton at pH 7. So this is the delta E0, or sorry, it's the E0 prime of a proton at 10 to the minus 7 molar protons. Okay, so that's a minor point. But all these other reactions, a lot of them involve protons. Those are all at pH 7. Right? So these are E0 prime values. From now on, we use E0 prime. I don't know that we'll ever use this equation, although it's a very important one, obviously. Okay. All right, the more important thing is, what do these numbers in this table tell us? Well, they allow us to figure out delta E values, which of course enables us to figure out free energy. Delta G's for reactions, which is important. But the other thing it tells us, in sort of a qualitative way, is the following. So if you look at the table, they put things with positive E values near the top and negative ones at the bottom. Anything that's up near the top is a strong oxidizing agent. Right? Another way that I always put it is that something like O2, it's a strong oxidizing agent. It's really good at accepting electrons. It has a high affinity for electrons. It really wants those electrons. Right? So O2 is at the top of the tables in biochemistry. It has a very large positive E value. Right? It has much higher affinity for electrons than does, say, H+. Right? And other things, iron plus 3 turns out to have rather high affinity for electrons. And some of these other substances. So conversely, anything that's near the bottom has much lower affinity for electrons. That is, anything down near the bottom with a negative, well, lower down in the table, really, is a weaker oxidizing agent. So it's always the substance on the far left that's the oxidizing agent. These are strong oxidizing agents. These are weak oxidizing agents. Note that NAD is actually a rather weak oxidizing agent. It's useful metabolically, but it's actually put in the oxide. All right, of course, the other thing is that if, say, NAD has low affinity for electrons, right? NAD can accept 2 electrons and become NADH, but it doesn't really hold those electrons that well, right? Another way to put it is that NADH is a strong reducing agent, right? So NADH gives up electrons pretty easily, right? So anything that's down here, the oxidized form is a weak oxidizing agent, therefore the reduced form is a strong reducing agent. And the converse is true up here. These are strong oxidizing agents. Once they've got their electrons, they don't give them up. So O2 accepts electrons to become water. Water doesn't give them up. Water is a very, very weak reducing agent. Right? So you have strong oxidizing agents, weak reducing agents, weak oxidizing agents, strong reducing agents. So a consequence of that is the following. Okay, so if you consider this reaction, so the reaction I'm indicating is the following reaction, one that we saw a while ago. If you consider the reaction in which NADH is a reducing agent and pyruvate is an oxidizing agent, so it's this reaction. So that reaction long ago, that fermentation can happen in muscle cells. On my figure, I said that NADH reduces pyruvate. What I mean is that if you had a mixture at standard state, so if you had 1 molar NADH, 1 molar pyruvate, 10 to the minus 7th molar H+, 1 molar lactate, 1 molar NAD+. I mean, what this table tells us is that this reaction would, and what I mean by saying reduces, is that this reaction is spontaneous to the right. In other words, the delta G0 prime is negative, right? And you could use the numbers in this table to calculate that if you were convinced, right? But that's sort of a little rule of thumb, that these are strong reducing agents, weak, relatively strong oxidizing agents, so that will be a spontaneous reaction. So the spontaneous reactions will involve reducing agents that are low in the table, reducing things that are higher up in the table, and higher up and farther to the left in the table that way. So cytochrome C, which we'll come back to probably not until it's time, cytochrome C will spontaneously reduce O2. The delta G of that reaction will be negative. So that's another way to sort of use these tables in a qualitative way. So one last example. This is the reaction that I started with today, or one of them. NADH acting as a reducing agent, O2 acting as the oxidizing agent. What this says is that you've got a strong reducing agent transferring electrons to a very strong oxidizing agent. So clearly that reaction will be spontaneous, at least under standard state conditions. All right, we could use this table, again, to calculate the delta G of that reaction. So let me just go through that very quickly again. So reaction is, we have happening here. So if we want to figure out the delta G0 prime for that reaction, we want to see whether the number I told you earlier today is correct. We can write the 2-half reactions. So the 2-half reactions we'll find are this one. E0 prime is plus 0.816 volts. And the other half reaction is going to be this one. E0 prime for this reaction so these are both for 0 primes, is minus what, 0.32? Minus 0.32 volts. All right, so we can use those numbers to figure out the overall delta G. By first figuring out delta E for the reaction. So delta E all right, we have these two, yes.
The product should be 1.
Pardon me?
The product should be 1 for the principal.
Yes, thank you. All right, so the delta E, to figure out delta E, we'll take this reaction. We don't have to turn it around, so we'll take its E, its reduction potential directly, plug it in. This is a reaction that we're going to have to turn around because NAD plus is the product of the reaction we're trying to figure out. All right, so it's going to be 0.816. Well, it'll be plus, change the sign. It's already negative. So it ends up being 0.816 plus 0.32, which is 1.136 plus 1.136 volts. And if you plug that into the equation, I'll finish it. So delta E is plus 1.136. So delta G 0 prime is going to be equal to minus N times F times delta E, which is minus. So N in this case is what? It's 2. That's the stoichiometry with which I wrote it. So N is 2. F is 96.48. And now delta E is 1.136. And this is equal to minus 219, I hope, which is kilojoules per mole. So you could use that for any of these reactions. You could use this to figure out the energy change of any reaction. That's why reduction potentials are very powerful, because they allow you to figure out delta G's for many, many reactions. Okay. Any questions? Everybody remembers all this? Sure. All right, so in the remaining 6 minutes, let me just sort of say a little bit more about what we're talking about. So I'm going to start on Monday with some of the details of the electron transport process. And after that, we'll do the proton pumping. So these are intimately coupled, electron transfer and proton coupling, proton pumping, but I'll do them separately. I'll just give a mention to Professor Leninger, who wrote the textbook, but his field was bioenergetics. So he was actually a pioneer in figuring out what's going on inside mitochondria. So he wrote the book. Actually, when I was in grad school, I used the second edition of the book that he actually wrote. Today, Cox and Nelson have taken his book, and now it's their book. They honor him by putting his name on it. So he was at Johns Hopkins. Okay, so he was interested in mitochondria, and so maybe I can just introduce and remind you what mitochondria are. In eukaryotes, this all occurs in the mitochondria. So if we could keep our focus for 5 more minutes. So mitochondria are a membrane-bound organelle. They have an outer membrane, which is porous. Right, it has large proteins that make pores, and so things can diffuse freely in and out. So the outer membrane is irrelevant from the standpoint of oxidative phosphorylation. It's the inner membrane which is the important part. So you have this folded inner membrane. And the space that's within that inner membrane, which is sort of an aqueous environment, a soluble, you could say, environment, is what's known as the matrix. All right, so this slide lists a lot of the important things that happen in these different places. The two that are important are the matrix and the inner membrane. So the inner membrane has the components for electron transfer, or for electron transport, and for ATP synthesis. And so we'll talk about next time, there's a number of proteins that are embedded in that membrane, and they carry out this process. And moreover, the proton pumping involves protons going from the matrix to what's known as the intermembrane space. So protons get pumped across that membrane. The matrix is where things like the citric acid cycle occur. Right, so the enzymes of the citric acid cycle are found inside the matrix of the mitochondria, which means that reactions like, well, NADH is produced in here. Right, so all the electrons are coming from the matrix of the mitochondria. Now, bacteria don't have mitochondria. And I'll show some slides next week of what's going on with bacteria. So if this is a bacterial cell, bacteria like E. coli have a cell membrane, and then they have a periplasm, and then they have an outer membrane. But if this is the cell membrane, the inner membrane, and this is the cytoplasm, the citric acid cycle occurs in the cytoplasm. The NADH is being formed in the cytoplasm. The electron transport components are in this membrane of the cell. And the protons are pumped from the cytoplasm outside of the cell. So for a E. coli cell, at least, protons are going from the cytoplasm to the periplasm. All right, so again, for E. coli, this is the inner membrane of the E. coli. That membrane is analogous to the inner membrane of mitochondria. So we'll see pictures of both. But I guess the focus would be on mitochondria. All right, so this is labeled at home. And so on Monday, I'll start with this very complex process, which is how these electrons get from NADH.